Okay. So 6.3, logarithms and logarithmic functions. Main thing, exponents and logs are inverses. And we're going to learn how to convert from one to the other here right off the bat. And it's probably one of the most important things you'll learn in high school math. And many of you will still not have it down very well by the time test time rolls around. But by the time you get out of high school, and high school math, you had better know how to convert a log to an exponent and back and the other direction. So here's the deal. We use the word log, and I suppose there are better ways to do this, but it's become conventional for everyone to do it this way, so that's how we're doing it. You write log, and it will have a base B, and it'll be a little one right there. It'll be just below the G as a subscript. You have a little B right there. Could be a number, could be a variable like it is right now. Of X equals Y. I think I'm going to do it the other direction. I'm going to replace the X and Y. Do it the way they did it. Make sure the variables are, yeah, Y and X. Okay, hang on a minute. This is new notation. It's very strange looking. I'll buy that. It looks really weird. This is how you pronounce it. The log base B of Y is X. The log base B of Y, there's a word of in between. It does not mean times like it usually does in math. It does not mean times. It's the log base B of Y is X or equals X. And it converts to an exponent this way. B to the X equals Y. Those two are exactly the same. These are equivalent expressions. Means you can write this and you can write this, and it means exactly the same thing. We'll graph exactly the same. These are equivalent. You can go from an exponential equation or exponential representation like this, and you can write it as a log, or you can write a log as an exponent. You have to be able to go backwards and forward. Now, let me show you how they're tied together. This base B right here, log base B, that's how you pronounce it, log base B of Y. This exponent over here also has a base of B. When you write an exponent, the big number that's being affected by this, that's the base of the exponent. This is the exponent, and together, we use it really loosely, but together, this expression right here, we're supposed to call that a power. Together, it's considered a power, but quite often we refer to it as an exponent. It's kind of a loose use of the words. But the base is never used loosely. The base of the exponent is this big number here, and it's a little number over here, and that's the anchor between the two. The base of the log and the base of the exponent are the same. And then, if you want to memorize how this goes, the X and the Y basically trade places. The X goes over here with the B, and the Y is the thing that gets isolated. This thing ends up over here, and this one ends up over here as the exponent. So you're going to have to practice going from one to the other. I'm going to leave that up there for a minute. And then we're going to try practicing on example 1, for example. It's an example. Log base 2 of 16 equals 4. This is what we've got to go with. Log base 2 of 16 equals 4. Convert that to an exponent. What is that equivalent to as an exponent?
2 to the 4th equals 16.
Good. Excellent. Which is true. And we're not asking if it's true. We're not asking you to solve anything. We're just asking you to write it in an equivalent form. And it's the base of this log raised to the other side of the equation, 4, equals what you're logging, 16. It's a true statement. We're not asking if it's true or false. We're asking you to convert its form. That's all. Does that make sense to you? All right, then without writing the next one down, the B part of example 1, we have the log base 4 of 1 equals 0. How would you convert that?
4 to the 0 equals 1.
I got a 4 to the 0 equals 1. The only person willing to speak. Is that true? And is, well, not only, is that correct form changing, and is it also true? Try the next one. What would you say? 12 is where you start. You start with a little tiny base. 12 to the 1 equals 12, which is true. Okay, the next one would be 1/4 to the negative 1 equals 4. I want to look at that one. After we've converted it over here, it's What did I say?
1/4 to the -1.
Oh yeah, 1/4 to the -1 equals 4. You might be asking, is that really true? Well, it is, because anything to the -1 it ends up being 1 to the -1 over 4 to the -1, and those two switch places. 4 comes up to the first, 1 comes down to the first, and none of these ones are necessary. Catch it? Okay. Now let's go the other direction. We're going to have an exponent given to us. We want to convert it to a logarithm. That gets a little, because this is new stuff. It's kind of weird stuff. Stuff you haven't written before. It's kind of hard to do right at first, but I think you'll get it. The first exponent we have given to us is 5 squared equals 25. So we're talking about this over here, and we're coming over to this direction, but I'm starting with it here. 5 squared equals 25. Can you tell me how you'd write that as a log? Log? Log what? Base 5. Make sure you include the word base so that you understand, so the people that hear you understand you. Log base 5 of 25 equals 5. I'm sorry, equals 2. Now this is just a skill that you may not understand why it's important yet. But you'll see later. I just want you to get good at the skill for right now, okay? And I will tell you, once you get good at it so that you understand that I can go from there to there and it doesn't take you a long time to figure out, or you keep going, I can't remember how to do that. You've practiced enough changing from one to the other that when it becomes important for solving an equation, that part of it won't be a hindrance to you. Let's try this one. 10 to the -1 equals 0.1. 10 to the -1 equals 0.1. By the way, do you believe that?
Yeah. Yes.
Isn't that 1 over 10? Because you put that downstairs, you put a 1 over this and make it to a positive 1. And 1/10 is 0.1, right? That's not the issue. What is it written as a logarithm? Log base 10. That's good. And that's a good way to say it. And it's the base of this exponent is the base of the log. And then of 0.1 is -1. Did you catch that? Everybody okay with that? All right, without writing the next one down, let's see if you can convert it. We're looking at the C part of example 2. Start out by saying log. Good. Log base 8 of equals 2/3. Do you believe that? 8 to the 2/3 means to cube root 8, which is 2, and take 2 of them. 2 of them multiplied, the other is 4. And the last one, this one's, I'm going to write this one down. 6 to the -3 equals 1 over 216. Let's convert that to a log first. Good. That's a good way to start. Log base 6, and don't forget to say, don't just say log 6. It's not log 6. It's not the log of 6. It's the log base 6, and that's different than logging 6. So log base 6
of 1 over 216 equals -3.
Good. You believe it? That thing, that expression right there, as you've learned, is 1 over 6 to the 3rd, and 6 to the 3rd is 216. So it's not only true, and that's the logarithmic expression that's equivalent to it. You guys think you can do this? Switch from logs to exponents and exponents to logs?
Yeah.
Think you can do that? You're going to get plenty of practice on your exercises. It's an extremely important skill. Luckily, it's not that hard, but you need to practice it so that it becomes second nature to you. All right, let's go to example 3. This one says to evaluate each logarithm. I'm going to tell you a cheap way out of this, but I'm going to show you the way that they want you to do it too so that you can understand it. We're going to use this same thing here, only it's not quite as clear how to use it when they ask you to evaluate. When you see the word evaluate in math, it means that your answer is going to be a number. And you got to figure out, looking at what they've written for you, what value does it have? That's why you evaluate it. Here's what we've got first. The log base 4 is 64. Now let me show you the way the book wants you to do it. And then I'll show you a way out, and then I'll show you an even easier way out. Okay? What they want you to do is convert 64. Well, no, they don't want you to do that yet. Hang on a minute. What you would do to use this stuff right up here, they give you this, they say evaluate that. I mean, it is a bunch of numbers, which means it has a value. But you may not know what it is. And so what you do is you insert an equals x, because I don't know what this is. It's going to be equal to something I don't know. Then at least you've got an equation to convert. What is this? After you write the equals x, what is this written as an exponent?
No. 4x.
4 to the x equals 64. And now you can start thinking of what you know about exponents. What do you have to raise 4 to get 64? 3. 4 times 4 is 16. 16 times 4 is 64. Or you can start checking things out on your calculator. You can take 4 squared, you know that's 16. That's not big enough. So you say 4 raised to 3, and you hit it right on. You go, oh, that's what it is. Well, this x right here is exactly the same as this x right here. So the value of this is 3. That's the answer to the question. Because 4 raised to this equals 64. It's this that you're supposed to find. Okay, now I'm going to show you something else that I'm not supposed to show you yet. We'll start back here with this. I'm going to start back here with just this part right here. This is the way it was expressed in the book. And what they would like you to do to evaluate this is figure out some number, 4 raised to some number equals 64. So what I'm saying is this. They want you to find an exponent. So we have log base 4 of 4 to the third. We just discovered that, right? It has to be this. It has to be this guy right here. 4 to the what gives me 64, and you put 3 here. What I'm trying to show you here is, and this is kind of new and strange and weird, but if you get an expression that's a logarithm where the base of the log and the base of an exponent involved, if you force that thing to be an exponent, if these two things match, you've got an exponent, base 4, and a log, base 4. If those match, they cancel each other out and just leave you with a 3. The reason they cancel each other out is because logarithms, that's this guy right here, and exponents are inverses. They undo each other. It's the same notion as this. The square root of x squared is x, because squaring and square rooting are inverses. They undo each other. If you write them in the same expression, they just undo each other and leave you with x. The same is true as if you have x squared and then square root that. You get x, because squaring and square rooting, regardless of the order you put them in, they undo each other and leave you with just x. Besides that, you learned earlier, and I'm going to remind you of this, you learned earlier that f of g of x, if that turns out to be x, then f and g are exponents.
Wyatt, grab your things, please.
Do you remember learning that? That if you compose f with g and get x, then that's for sure that f and g, well, you have to do it the other way around. G of f of x also equals x. If you get both of those equal to x, then g and f are inverses. And look, if you take x squared, if your f is root x and g is x squared, then if you stuff f into g, you're stuffing root x in for x, and you get root x squared, which gives you x. If you stuff g into x, you're stuffing x squared into x right here, and you're square rooting x squared, which gives you x. That's verification that they are inverses. Well, I just told you that logs and exponents are inverses. So if you've got a logarithm with the same base as an exponent in the same expression, they undo each other, leave you with what's left over here when you have the same base. So what they're trying to do is get you to convert 64 as 4 to some power. Then you have a log base 4 of 4 raised to this thing and the thing. That's the answer. In a general way, then, for as far as logarithms and exponents go, with this whole monster discussion here, if you have the log base b of b to the x, the answer is x. Now, do you remember with the square roots? I should have erased them all. Do you remember with the square roots, if we have this and square it, we get x, but if we do it in reverse and we have x squared and square root it, we still get x? Because it doesn't matter which one you stuff into which one. Well, this expression right here, written the other way, would be this way. B to the log base B of x, that's still x. Because I have an exponent and a log with the same base. These guys undo each other, leaving you with x. These guys undo each other, leaving you with x. And it doesn't matter which one comes first. As long as the base of the exponent and the base of the log in the same expression are the same, then you're left with this x in both cases. It looks weird. It looks strange, but it's the same concept as that, composing functions. And it doesn't matter whether you put the exponent inside the log or you put a log inside an exponent. If they have the same base, they're going to cancel each other because they're inverses. Follow that? Okay. Here's another way. Well, no, I'm going to teach you that way. Not yet. It's coming up in the later section. But you'll learn how to evaluate this thing that we started out with. You will learn to put that in your calculator, and it will kick out a 3. And you won't need to know any of this stuff to get the problem done or check it. But this is still really important stuff when we are dealing with variables. And we can't put it in the calculator. But there's a way to evaluate this in your calculator, even though you don't have a log base 4 key. I'll show you how to do that later. All right, so let's take a look at example 3. It says evaluate each log. We got 3 for the first one. Now look at the B part. 5 to the what would give you 0.2? That's the question. We have a log base 5 of 0.2 that we're supposed to evaluate. The log base 5 of 0.2. We don't know what it equals, so I'm going to write x. What could you raise 5 to? I'm changing this log to an exponent. 5 to the x equals 0.2. It'd be a lot easier for you to figure this out if you wrote 0.2 as a fraction. 1/5. What must x be? -1. Because if it were -1, that would shove it downstairs with an exponent of 1. So if you've got a decimal and you can't figure out what that is, you can change it to a fraction. It will take on this same sort of a situation. It'll be a lot easier to tell what it is. Okay? You following? So the trick to evaluating these things is to write equals x. Then change that log, that equation, that logarithm, change it to an exponent and see if you can figure it out. Okay? Let's try the next one. The log base 1/5 of 125. What do you think? Without looking at the solution, I know that's where your eyes went as soon as I told you that. The log base 1/5 of 125. How should we begin? Equals x. That's the first thing I would do. And then you've got this situation. What we change it to? 1/5.
Or 1/5, sorry.
Raised to the x equals 125. Wow, that's going to be pretty rough. You can see the relationship between the 5 and the 125, can't you? Would you agree that this part in here is the same thing as 5 to the -1? Oops, raised to the x. You understand that little move? And then your rules of exponents say that you can multiply these two. That's 5 to the -x equals 125.
Blaze here. Yes. Wait then.
Who?
Blaze. Bring that is here.
Yeah.
Fine, yes. When you wait.
Yeah.
We're getting closer. I mean, this took a lot of work just to get to here. We know that to make this 125, this number here has to be a 3, doesn't it? So -x equals 3. So x is -3. That's a lot of work to get there. We first wrote equals x. We changed that whole logarithm to an exponent using this little rule right here. And then we got stuck and got a fraction equal to a whole number. So you work inside here to change that to a whole number, at least I would. I mean, not a whole number, a fraction, by taking that which was raised to the 1, taking it upstairs, 5 to the -1, then apply that little rule which makes it -x, and then you look at this, you go 5 to something's got to be 1. I know that's got to be a 3, so you write it down. That thingy has got to be a 3, solve it, get -3. It's pretty crazy. You can get really nutty pretty quick. And the last one, the log base 36 of 6. How should we begin? Equals x, now convert it.
36x equals 6.
Anybody? Know what it is? Not 2,
That'd be a
close.
half because you have to one half.
Would be a half, because we gotta get the 36 to turn into a 6. In other words, we know that the square root of this has gotta be 6. We also know the square root is the same thing as a half. Right? As written. So this is 36 to the 1/2 equals 6, and so the answer is 1/2. Did you catch that?
Yeah.
That can be a little rough too, but you gotta remember your exponents and your square roots are related. Holy moly, I've got a ways to go here. Oh, actually, I've already taught you most of this. All right. Example 4, super easy because it's calculator exercise. They just want you to get used to the buttons. That's all. So if you look at example 4, it says evaluate log 8 and the natural log of 0.3 using a calculator. Except there's something really, really important I forgot to tell you. Got to tell you this first. It's not a big deal, and it won't take very long. There are 2 extremely important special logarithms, and they're so important and special that all scientific calculators have keys dedicated to these 2 logarithms. Log base 10, because we have 10 digits on the ends of our arms. We have a base 10 decimal system, so we have logs base 10 because of that. And this right here, the log base 10 of x, is exactly the same thing as the log of x. When you see no subscript there, it means 10 by default. Just like this does not have a 2 in it, because we use this so often. It's not written. We all understand it means 2. You know what I mean? Okay, so you won't see log base 10 from now on. If they mean log base 10, they will just write log, and we will say log 10. Also, and another extremely important logarithm for natural growth things is log base e. And we don't write log base e. We write ln. And that means log base e. It's pronounced natural log. And people say, well then, why isn't it NL? Because you are speakers of English, and in our arrogance as English-speaking Americans, we believe that everyone speaks like we do, and really our language is way different than everybody else's in the world. Just about every other language that I've ever had, I don't study languages, but I know enough about languages that all the other languages, especially European languages, when they speak, they always put the noun first, the adjective second. We always say, we would drive down there and see that red barn? They would not. They would say, see that barn that's red? They tell you what they're describing before they describe it. We tell you what the description is before we tell you what you're describing. And we are the unique, rather strange ones. And since most of this mathematics we're studying here was developed in Europe, that would be pronounced logarithm natural, meaning they're describing the logarithm as being natural. They tell you the noun first and the adjective second. But we, as English speakers, say natural log. It's describing what kind of log it is. It's a natural one, like the red barn, instead of the barn that is red. But because Europeans developed it, we will adhere to their way of writing things. So when you see this, we pronounce it in English as natural log. However, it will be written ln. And the keys dedicated to these 2 things on your calculator are right here and right here, right here and just the one above it. So kitty corner to the 7 and the 4, those are your log keys. The log key is log base 10. The ln key is log base e, which is natural log. So take a look at example 4. It says evaluate the log of 8. So you type log first. You hit your log key and it opens a parenthesis. Type in 8 to close it. And then, do you have to close the parenthesis? No. But it's an excellent habit to get into because in the future you will have logs of several different things in the parentheses. You want to make sure you close it before you do anything else to it, like add a 1 or something. You want to make it a habit to close those parentheses. So you get 0.903?
Yeah.
Okay, that was easy. And also use your calculator to evaluate the natural log of 0.3. So it's your natural log key, put 0.3 in parentheses, close it. And you get negative 1.204. Easy, right?
Yeah.
Just wanted you to get used to that notation. Log without a base is base 10. And ln, a very strange thing, is a log base e. So when I ask you to evaluate something, we did that appropriate e. All right, example 5. This is the one that I've already taught you. And since I already have, it should go pretty quickly. Look at example 5. It says simplify 10 to the log 4. 10 to the log 4. What's this base? What's the base of this? 10. What's the base of this? 10. So the answer is 4. Because you got an exponent base 10 and a log base 10 in the same expression. They undo each other because they're inverses, leave you with a 4. But the reason why they threw this one at you is because you got to remember that this is an understood 10 here, so that you can see that these are both base 10. Okay? Next one says to evaluate or to figure out the log base 5 of 25 to the x. This one's a little more convoluted. Log base 5 of 25 to the x. You're thinking, well, those aren't quite the same. But they could be made the same pretty quickly and easily. Meaning, I could write this as 5 squared, that 25, so that these match. That would be 5 squared to the x, which is this. And so the answer is 2x. Because the log base 5 and the exponent are base 5. And you're left with this. Y'all following? Yeah. The cancellation? But you got to convert it a little bit. These aren't quite the same base. But you can make them the same base and apply this little rule here and get a 2x out. Probably do most of that in your head if you understand what's going on. Okay? Example 6. We're almost done here, folks. Hang in there. This time we are going to find inverse functions, and we're going to use this guy right here to make it happen. And if you'll remember from the previous chapter, finding inverses of functions means you switch x and y and solve the new thing for y. Do you remember that? Do you recall that or not really? I'm going to show you how we did it before with stuff that you're familiar with. If I have an original function, f of x is equal to 2x squared plus 3, and you are to find f inverse, then the first thing you did is call that y. And a lot of people didn't even write this step down, but I'm going to write it. And then switch places. That's finding the inverse, remember? And then once you've switched places with them, then you resolve this thing and get y by itself by first dragging the 3 over, then dividing by 2, and then square rooting. And calling it f inverse. It's actually plus or minus. That wasn't a very comfortable example, but do you remember doing this? We do the very same thing here. We're going to take logarithm and exponential equations and find their inverses. The first one is f of x equals 6 to the x. Following the same strategy, f of x equals 6 to the x. First thing I do is call this a y. Then switch places. Then solve for y. You go, how the heck do I solve for y? You have something like this, convert it to that. Anybody? I know everything's a little backwards, I've got these things on the wrong side, and I've got x's and y's mixed around, but see if you can follow the pattern, convert that to a logarithm. Log, not of,
Base.
log base 6
Y
of x equals y. What this does, folks, if you'll take a look here, notice what happens. If I have an expression like this, look at this one over here. Didn't it isolate the x? Didn't it isolate this weird old looking thingy up there that you can't access? It got it all by itself on one side. Same thing here. It's this that we want to get on one side, and changing to a log does it perfectly. And call it f inverse. So f inverse of x is the log base 6 of x. That's pretty tricky. it's when you get to here, and you switch places with x and y, right here, the switching right here, you go, crap, I don't know how to get at that y. There's no algebraic way to get at that. There is now. There is a way to get at this thing with a logarithm by changing it to a log. It's a way of isolating this thing up here in this little ivory tower that you couldn't touch before algebraically. Now we can. And by the way, a study of exponents and logarithms and how they're related, these are now called transcendental functions. These are transcendentals. And the reason why they are transcendentals is because they transcend the algebra skills. They go beyond the algebra skills that you have. Because you do not have the algebra skills to isolate y. There is no way to get y by itself algebraically. And it became necessary for people to be able to figure out what this value was in any situation, be able to solve for it or whatever. And so they had to invent or transcend the algebra that they knew. And they developed a whole bunch of logarithmic scales, they call it, to do this very thing. So this is a transcendental move right here. You have to change the exponent to a logarithm using these patterns. And going from an exponent to a log isolates the exponent. And the exponent in this case was y. So y is what got isolated in the logging. Do you see it? Cool. Okay. Next one is a logarithm, and we want to change it to an exponent. We have y equals the natural log of x plus 3. This is where it starts. Y equals the natural log of x plus 3. Now, they've already changed the f of x to y for us. Okay? So we're already at this stage right here. And now we got to switch places with x and y, and we get x equals the natural log of y plus 3. And our goal is to solve for y. What do we do? Change that logarithm to an exponent. We have a log, change it to an exponent. What's the base of that log? What's the base of the logarithm I'm looking at here? E. It's understood. You got to know in your mind that there is an E right here. Little E right there. So now change that. How do you know that that's an E? Change that log to an exponent. E.
Raised to the y plus 3.
No.
Plus 3.
Look. E raised to the other side. Remember? E raised to the other side. E raised to the x equals y plus 3. Now it becomes algebraic. Kick the 3 over. That's your inverse. Crazy, huh?
Yeah.
If you start out with a logarithm and you're going to find the inverse right here at this stage, after you do the switcheroo, you got to change that log using the inverses. You got to change that log to an exponent. This base raised to the other side of the equation equals what you're logging. In this case, the stuff that you're logging is what gets isolated in the move. And then if you haven't quite got y by itself at that point, then you bring that over out. Now it turns into algebra, and you get this y by itself, this new y. Do you need to practice one or two? Or try a couple of those? Because this is probably the toughest part of the assignment. Yes or no? Want to try it? Okay. There is some monitoring progress at the bottom of page 312. No, I don't like it. Oh, wait. 17 and 18. The last two questions on the bottom of page 312. 17 and 18. See if you can do those. And try not to look up here. Well, actually, I'm going to erase these. Let's see if you really can do it. I'll leave this up here, this changing. Please don't look back at the examples either. See if you can do it by yourself from scratch from what you just learned. you need some help, that's why we're practicing this. Let me come to your desk and help you individually with your individual situation, if you need some help. $17 or $18? Huh?
So,
Yeah.
that's it.
That's it.
But what is the X number right there? That's it. That's the other side.
Well, you have to switch places. You gotta switch places.
Oh,
Then you go to that and it converts this way.
okay. All right.
Yeah, that way. Try that. Anybody have the first one?
I think I might.
Okay, tell me.
Is it log to the base of 4 of x equals what?
Find out.
That's what we got, yeah.
Everybody get that? Y equals log base 4 of x? Okay. Anybody have an answer to 18?
That e to the power of x plus 5 equals y.
That'll work. Y equals e to the x plus 5. The whole thing plus 5. Not plus 5 in the exponent. Anyone not get that or need an explanation of that? Anybody?
I need an explanation.
On the 18?
Yeah.
Okay, so first thing you do is what?
Change the place of y.
Right, so we have x equals natural log x minus 5. Y minus 5 is what I meant to say. Is that correct? Now we got to change the log to an exponent. What's the base of the log? That's the first thing you got to discover. What's the base of the log?
E
E. So it's e to the what?
to the x.
X equals
Y minus 5.
y minus 5.
Move it over.
Then get rid of the 5. Follow that?
Yeah.
Yeah? You think you can do this? Okay. Last thing, and this will go quick. I just want to show you how you could graph this if you were asked to graph it. Because if you go to your y equals screen and you want to go to type this in, you don't know how to do it. You don't know how to graph that. However, we do know that logs and exponents are inverses, right? So what if I changed this thing like this to an exponent by taking 3, well, change places with x and y first. X equals log base 3 of y. Change that thing to an exponent and graph that. And then reverse all the x's and y's because they are inverses, right?
Yeah.
So I could do this. That wouldn't be too bad. If I just did some points on here, I could graph it on that without ever using my calculator. Or I could graph this and go to my table and switch places. I'll show you that real quick in a minute here. If I put -2, -1, 0, 1, and 2, 3 to the -2 is the same thing as 1 over 3 squared, which is 1/9. Pretty tiny, but still positive, right? 3 to the -1 is 1/3. 3 to the 0 is 1, like everything is. 3 to the 1 is 3. 3 squared is 9. You all think you could come up with those pretty easily? And then you would plot those, or if really what they wanted you to do was to graph this, if you changed it to this and then, if you inverse of it right here and got these, then what you'd really be plotting is the point 1/9, -2, and 1/3, -1, because inverses switch places. So to graph this logarithm by hand, you would plot 1/9. So here's the origin. 1/9 is barely out to the right, and then down 2. So it's right here. And -1 and 1/3, no, sorry, 1/3, out of third, and down 1, so it's barely out from there. And then 1, 0, out 1, up 0, and then 3, 1, 1, 2, 3, 1, and then 2, 9, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2. So this thing looks like this. Goes out like that, whereas the original function looks like this. You're just going to trust me on it. Goes like that, and sure enough, they are reflections of the line y equals x as all inverses are. So there is a way to graph this without putting it in your calculator by changing it to an exponent like this and graphing this, y equals 3 to the x. Now in your calculator, if you do that, y equals 3 to the x, you have to get to that point. You graph y equals 3 raised to the x, and then if you go to your table here, you go second, once you get that in there, I have to hit enter. You go second and table, it will give you a bunch of points. But you gotta remember to reverse them. Because you're looking at the inverse on what you want to graph. So you would plot the y and then the x and y and then the x, which I did with the pink there. There's a way to get it graphed by hand if you refer to the inverse, which you can graph in here, and it will give you a bunch of points without having to do the figuring on this table. You just go to this table. But you gotta remember it's yx, 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 yx that you plot to graph the logarithm. Okay, first page, and we're finally done. Mostly about using this. I would write this on the top of your page so that you can refer to it quickly without having to look it up. But as you do this exercise, get this committed to memory to where you don't have to look anymore, because you do not get that on the test. You have to know that is an extremely important thing. For those of you doing this assignment on paper, here's the assignment. 3 through 23 odd. 27 to 53 odd, and 61 to 65 odd. And if you think that's a lot of problems, you're right. 28 problems to do. This is really important stuff that you get really good at converting from exponents to logs and vice versa. There we go, folks.